Okay, welcome to Chapter 5, Part 2. So in this section, we're going to talk a lot more about stereoisomers. So we know isomers are same formula but different compounds, and that can be split into constitutional, which is same formula, different connectivity, versus stereoisomers, which is same formula, same connectivity, different orientation in space. From here, there are a couple other types, and we're going to go through those, or at least one of those in this video. We are going to talk about something called chirality in this video, and something that can be very helpful are modeling kits. So if you did get a modeling kit, this is the chapter to pull it out. If you didn't, I'm going to link some videos as well that incorporate people using actual models, because I think that's important. And I encourage you to come use the models in the lab when you have a chance. Okay, so let's just get through some vocabulary here. A chiral object is asymmetric. It is not the same as its mirror image. So actually, let's define this a little bit nicer here. Okay. Chiral objects. So we're going to discuss this in the macroscopic perspective and then microscopic. Macroscopic and microscopic. Chirality just means that it is going to be a non-superimposable mirror image. So there is some sort of asymmetry that when you reflect this object through a mirror, that mirror image is not superimposable. So one of the easiest, examples we can think of that I usually talk about in class are your hands. So forget any sort of birthmarks or freckles or scars or, small inconsistencies like that. Think about the shape of your hands. When you put your palms together and then kind of separate them, they are mirror images of each other, right? The thumbs line up, the pinkies line up, everything in the palms line up. But you cannot flip your right hand over and make it the same as your left, right? The nails are either in the wrong place or the thumbs are in the wrong place. They might be mirror images, but they are non-superimposable. And there's a lot of chiral objects in the world. If you think about a few examples that come to mind, if you've ever been left-handed and tried to use most scissors, or been right-handed and tried to use left-handed scissors, you know they're not the same. They are mirror images, but they're non-superimposable, and it makes a big difference in their utility. If you think about desk chairs growing up, the type of chair that has the desk come out, and you have a left-handed one and a right-handed one. They're mirror images of each other, but they're not the same thing. They're not superimposable on each other. Well, we have that experience with molecules as well. Chirality is important for a couple of different reasons. Since it's the same connectivity but different orientation in space, they can have very similar physical properties, but their pharmacology, some of their chemical ways that they behave might be different. That can be very important. We're going to talk about that. Let's see. I think Klein is absolutely correct. It is critical that you look at a handheld model. So again, if you don't have your own, stop by my desk in lab and check out some of mine. One of the easiest ways to make this for yourself is to make these two models. Put a black carbon in the middle, and any modeling kit, the black atoms represent carbon, and they should have 4 places to connect to make that tetrahedral structure. Put 4 different groups onto that carbon, and then build a second model that is a mirror image. There is no way that you can turn or flip or roll this one around that will make it identical to this one. if you look at this, the blues are going out to each other, the greens are coming out towards us. If I turn this molecule around so that the blues and the red will stay lined up and both blues will be pointing, to the right, well, now this green will migrate to the back. So there is no way to twist and turn this one on the right and make it into the one on the left. That makes them different. That gives them some different properties. And so these are considered chiral compounds. They are stereoisomers of one another. Some examples of what the different colors could be. You see a real example here. You have a methyl group, an ethyl group, an alcohol, and a hydrogen. As long as it's 4 different groups, you can find this type of stereochemistry. Now, it has to be 4 different groups. So in this case, all of the examples that are highlighted are called chiral centers. We are looking for, when we talk about a chiral center, we are looking for carbon with 4 different groups. And we aren't just talking about a single atom, we're talking about the whole group. For instance, look at this first one. You have chlorine. There is a hydrogen that's not being shown to the back, and then there is a 1 carbon chain and a 2 carbon chain. So we would say that that is a chiral center. On the next one, you have a 2 carbon chain, a 3 carbon chain, an OH, and an H. 4 different groups. Rings can sometimes be tricky to folks. This example is a chiral center because if you go up, you have bromine. If you go up into the back, you have hydrogen. If you go to the right, you have a carbon double in a double bond, carbon in a double bond, CH2, CH2, CH2. But if you go to the left, it's the opposite. So each path is different. So it is 4 different groups. So all of these green highlighted atoms are chiral centers. Something I want to point out is the symmetry does matter. If I had something like this, a bromocyclohexane instead of one with a double bond in it, this is not chiral. There is not a chiral center here. And the reason is you do have a bromine and you have a hydrogen, but if you go down the right path or the left path, it's identical. It's 5 CH2 groups. So it is the double bond over here that is causing this one to be chiral. Right, so carbon with 4 different groups, and it has to, for it to be achiral, and so achiral means not chiral, then 2 of the groups will have to be the same, like you see in this example here. Now, how many chiral centers? It can be easier or harder depending on the type of representation you might have been given. And so you might see chairs, you might see bond line structure, you might see Lewis. But let's go ahead and take a look. We get 3-dimensional information on the chair because we have up versus down, and we get wedges and dashes on our bond line structure. Sometimes people jump to the conclusion that a wedge or a dash means you have a chiral center. And we're going to see that's not always true. So in this first one, you have 1 chiral center, or you have no chiral centers. No chiral centers. Because even though this carbon has an H and an OH, going up and going to the right are the same. It winds up being CH2, 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 CH2. So there are no chiral centers in that first one. In this second one, however, both of these are chiral centers now. So now why is that? Well, we still have that H going down, but now if we go up, we meet a carbon with an OH on it, whereas if we go over here to the right, we meet a CH2. So the paths around are not identical. So this one winds up having 2 chiral centers. In this example down here, again, we only have 2. And the reason is, look at all the groups, right? We have a methyl coming or going away from us. That means there would be a hydrogen coming towards us. On one side, there's an isopropyl, and on the other side, there's a sec-butyl. If we look at the right highlighted carbon, we have a methyl, we have a hydrogen that's implied, we have an ethyl group, and then we have whatever the heck that is. Right? They're all different. Now, the mistake some people want to make will be to highlight this one. That is not a chiral center. You have, and let's get rid of this H here because it's confusing. There we go. You have a methyl group and a methyl group, a hydrogen, and then whatever the rest of that is. But there's two methyl groups. If these two are the same, then that can't be a chiral center. There has to be 4 different groups. So this one only has 2. And then the next one also has 2. Both of these are chiral centers. The 4 groups are indeed different. And so I think the next slide will just verify that. So none, 2, 2, and 2. There will be some practice on your homework, practice in old exams, in identifying chiral centers. Some molecules have a lot of chiral centers, especially large biomolecules. Here we're looking at vitamin D3. We are being asked to identify the chiral centers. I'm going to go quickly, but pause here and try this on your own. Anything that's a CH2 is automatically not chiral, right? H2, 2 of the things are the same. So going around this ring, we have one here, because going left and right around that ring are not going to be identical. None of your carbons in double bonds will be a chiral center themselves, because you can't have 4 different things if you have a double bond. So that's the only one in that ring. But in the next bicyclic piece of the structure, we have 1, 2, 3. All 3 of those, if you look, have 4 different connections, either to H's or methyls or different pathways around asymmetrical rings. Then we also have this one here. And that's it. The branch on the end, right, these are both methyl groups here, so that one doesn't work. So in the end, we have 1, 2, 3, 4, 5 chiral centers. When we are talking about these non-superimposable mirror image molecules, the name of these 2 stereoisomers is called enantiomers. That is not what I wanted to do. There we go. Enantiomers are the non-superimposable, so not identical, mirror image compounds. And there's a few different ways to draw them. You can reflect through a horizontal or vertical mirror. Here we're just going through this this vertical mirror. So we're going to draw the mirror image. And there is no way to flip this guy around, because if we take the straight chain and we flip it over, the chlorine will be on the right position, but it will be going to the back. It'll be dashed, right? So these are non-superimposable mirror image compounds, otherwise known as enantiomers. That is an important word you should know. You can also, and I don't know, you could also easily flip it through a horizontal mirror, and sometimes you'll see that. Let's see. 2, 3. And then this would be down here. It's the same idea. You just have to think about, could you flip this over and make it the same thing? You also might see, as we move along, another way to do this would be to just switch the wedge and the dash. All right, that will also give you the enantiomer of this guy. So there are different ways to draw the enantiomers, and you'll be practicing with them throughout this chapter. All right, so examples of enantiomers. Examples of enantiomers. Just different ways to draw them. But you wind up with all the same connectivity, but a little bit different orientation in space. These are not these are not enantiomers. These are identical. And again, it's because this CH3 is the same as this CH3, right? You can't have a chiral center if you don't have 4 different groups. Now, in the next video, we're going to talk about how to handle chiral centers in naming. They do have some different properties, so it is important that we are able to give them different names. So see you in part 3.